Hello students, in this video we are going to learn about numerical aperture of an optical fiber. What is the meaning of numerical aperture? It is the light gathering capacity of an optical fiber. Means how effectively the fiber is conducting light energy from one end to other end. It's basically taking the light signals effectively from one end to other end. So we'll see the geometry. This is the core of the optical fiber. This is cladding. Core is having refractive index N1, cladding is having refractive index N2. And the dotted line here is indicating about axis of the fiber. Let's consider ray of light incident from the interface medium to fiber. An arbitrary angle will take. Let's take this angle is theta naught. If a ray of light incident from rarer medium to denser medium, the ray would bend towards the normal. And here the medium is air having refractive index N0. This ray will bend towards the normal and it will incident at core and cladding interface. This is core and cladding interface. Which one is this? Yeah. The green line here is indicating the interface to core and cladding. Let's say this angle is IC and this angle would be 90 and this angle will be 90 minus IC. This you take it as point A, point B, point C. Here the blue line is indicating about interface to rarer medium and core. The blue line, one more line I am drawing here, that is along the axis of the fiber, will work as normal. So we are taking the incidence angle with respect to the fiber axis. If this is the geometry, let us see, IC have written saying that here the incident angle is critical angle. It's becoming critical. Meaning is that the refracted beam will make an angle 90 with the normal. So refracted beam would go like this. If you apply Snell's law at point A, and at point B, we are gonna get so apply Snell's law for two pair of mediums. At point A means we are going to apply first for the incident ray here in the rarer medium. The refractive index of the rarer medium is n naught and the sine of the angle in that medium is sine theta naught will be equals to the core refractive index. It is n1 and the sine of the angle in that medium is 90 minus IC. We can further simplify this as n naught sine theta naught is equals to n1 sine sine 90 minus theta, so this will become cos IC. Now let us apply Snell's law at point B. This is the point B. So what we are going to get? At point B. Here the incidence ray will be in the core medium and the refracted beam will be taken in the second medium, that is rarer medium. So the core refractive index is n1 and the sine of the angle in that medium is IC. So sine IC is equals to, the next medium here is n2 for the cladding and sine of the angle in the cladding, that is 90, because this incidence we considered as the critical angle. We can further simplify this, will be equals to n1 sine IC is equals to n2 sine IC is equals to n2 upon n1. Call this equation as 1, call this equation as 2, call this equation as 2, call this equation as 3. So from equation 2 and 3 we get, put sine IC into equation 2 after converting cos IC in terms of sine. So this equation I am taking as is equals to n naught sine theta naught is equals to n1 cos theta can be written as 1 minus sine square theta, that is IC, raised to half square root, because sine square theta plus cos square theta equal to 1. Now we substitute the equation 3 in this instead of sine square IC. So this will become n naught sine theta naught is equals to n1 1 minus n2 square upon n1 square raised to half. Further we are going to get n naught is equals to sine theta naught is equals to square root of n1 square minus n2 square. Sine theta naught is equals to square root of n1 square minus n2 square upon n naught. N naught is the refractive index of the air, the interfacing medium to fiber cross section, and this is if the incident angle in the interface medium is greater than to that, will not reach to other end. This maximum angle is known as theta naught max, is known as acceptance angle. What is acceptance angle? It is the incidence angle or the maximum incident angle in the interface to the fiber, which will help the light ray to suffer total internal reflection inside the fiber, and as a result it will reach from one end to other end. Now, if a ray falls from here also, if this is theta naught max equals to, then this ray would go the same way how this has got suffered, and this would go total internal reflection in the same way. So here particularly I am talking direction does not matter. That means from which orientation the ray would fall, from which orientation. So if I can form this 360 degrees, that means if I can rotate this ray to 360 degrees, it will form a cone. This is also known as cone of acceptance. In a solid form, in a 3 dimension, we can also tell this as cone of acceptance. Meaning is that any ray which falls within the cone will reach to other end of the fiber. If any ray falls out of this cone volume, it will not reach to the other end. Rather, the ray will penetrate, refract into the core cladding, and it may come out, and the energy is wasted. So the condition we have understood here. So what with this condition, when theta naught tendings to theta naught max, that is equals to, for the zero ray I am talking, the ray would give me total internal reflection. That means it is conducting the light. That means effectively it is conducting. Then the sine theta naught max, because theta is becoming theta naught max, then this formula here, sine theta naught, I would write it as sine theta naught max. I am calling this parameter is equals to or equals to NA, that is numerical aperture. So now I will write NA is equals to square root of N1 square minus N2 square upon N1. I'm sorry, this is N naught. For air, the refractive index N naught is equals to 1. Henceforth, we are having NA is equals to N1 square minus N2 square. That means the numerical aperture of an optical fiber dependent on three mediums. What are those three mediums? The interfacing medium to the fiber cross section. What is and its refractive index, and the core refractive index, and the cladding refractive index. And we know for an optical fiber to work properly, this must be satisfied. N1 is greater than N2 always. Otherwise, total internal reflection inside the fiber is not possible. So we have seen this numerical aperture formula as square root of N1 square minus N2 square. There is one more parameter which we need to understand. It is about delta. It is also known as fractional refractive index change. So another alternative formula we need to find it for numerical aperture in terms of delta. The delta is taken as N1 minus N2 upon N1. So using this expression, we want to convert NA in terms of delta. We'll look it in the other video. Thank you very much. In this lecture, we learned about what is numerical aperture. We have seen the derivation for numerical aperture by applying Snell's law at 2 points, point A and point B. And we have seen what is acceptance angle theta naught max is known as acceptance angle, and we have seen the ray when you take it in 360 degrees, if the incidence orientation, then cone will be formed, and that is known as cone of acceptance, within which when the ray of light falls, light would suffer the total internal reflection and fiber will be conducting light effectively from one end to other end. Thank you very much.